Hi everyone. What we're going to do in this video is talk about Lewis structures. Lewis structures, these are electron dot representations. Now, although we're calling these electron dot representations of molecules, but sometimes we could also use a bond to show the electron pair. Okay, so what the Lewis structure does is it actually gives us the connectivity in a molecule. And what I mean by this is it actually tells us how the atoms in a compound or a molecule are connected to each other to make that molecule. Now, sometimes you would realize that there are different possibilities. So we'll go into that also. But let's lay down the ground rules first, okay? So what are some of the ground rules that we need to follow? So when we are discussing the Lewis structures, we should consider only the valence electrons. So this is very important. So for example, carbon, it has an atomic number of 6. That means it has 6 electrons, but it has only 4 valence electrons. So we're going to consider only the valence electrons when we talk about Lewis structures. The second important thing is not maintain, we'll just say octet rule. So consider the octet rule always. That means elements in the second row, and this is important because most organic compounds that we will be encountering or will be discussing would comprise of carbon, oxygen, nitrogen, hydrogen, etc. So for those, the octet rule must be obeyed. Okay, so for the second row elements, no more than 8 electrons. Now, for the hydrogen, only 2 electrons should be there. Okay, so hydrogen, it maxes out at the octet at 2 electrons. So 2 is where we're going to stop. And as we build these structures, something that you might want to remember is that hydrogen, it can only form one bond because it only needs 2 electrons to satisfy the octet rule. That means hydrogen cannot be inside a molecular structure. So it cannot be bonded to more than one element. Hydrogens always appear on the periphery. So they basically end over there. So if you're building a few bonds or making bonds between several atoms, then when a hydrogen shows up, that's where the bond is going to end. Okay, so they're usually on the periphery. You cannot include a hydrogen somewhere centrally in the molecule or more than one bond. That should not happen. So only one bond to hydrogen. Now, before we start building Lewis structures, we need to remember some common patterns, okay, for bonding. And again, we are concerned mostly about the second row elements here. So the common patterns, the bonding patterns for the elements that we are interested in are hydrogen is one element that we are interested in. It is only one bond. Carbon is going to make 4 bonds, okay? So a carbon is tetravalent. It will form 4 bonds. Now, it does not have to form bonds to 4 different atoms, but carbon generally forms 4 bonds. Nitrogen, similarly, has a lone pair on it, and it will form 3 bonds. And oxygen will form 2 bonds and 2 lone pairs on it. Any halogen, X, we will use X to represent halogens. Any halogen is going to have 3 lone pairs on it, and it's going to form 1 bond. Okay. Now, these common bonding patterns, these apply when there is no charge on the atom. Okay. So if a carbon has a positive or a negative charge on it, this is not how its bonding pattern is going to be. And the same applies to nitrogen, oxygen, or halogens. Okay. So these are when there is no charge on these atoms inside a molecule or a compound, then this bonding pattern will apply. Okay. Now with those ground rules, let's go ahead and develop some Lewis structures, and we'll talk about other other sort of rules or other guiding factors that should be kept in mind. Okay, other things that you would like to consider. With those ground rules in hand, let's think about a structure or a molecular formula, which is CH4O. So this is some compound which has 1 carbon in it, it has 1 hydrogen in it, and 1 carbon, 4 hydrogens, and 1 oxygen in it. And we're going to build a structure for this molecule. Okay, so one thing you would do is, before you start, just count the number of valence electrons, total number of valence electrons here. Total number of valence electrons for the system. Carbon has 4 valence electrons. Each hydrogen is, so carbon is 4, hydrogen equals 1, oxygen equals 6. And we have 4 hydrogens, so that will give us a 4. So we have 4 plus 4 plus 6, a total of 14 electrons. So that means this system here has 14 valence electrons. Now, if your molecular formula has a charge to it, if there is a positive charge, then you're going to subtract an electron for every positive charge that's on your system, the given molecular formula. Similarly, you're going to add an electron for every negative charge. So for example, if this whole system was CH4, but now with a positive charge on it, if this whole thing was positively charged, I would remove 1 electron from these 14 electrons because there is a positive charge. Okay, that's how you would do it. So we get CH4O. So now we have the number of valence electrons. The second thing we're going to do is, now we're going to arrange these atoms in a, using a pattern that we think that they may be bonded to each other in. So, it could be anything, and this is like hit and miss, trial and error sort of a thing. So you have to try. So, but since there's carbon, 1 carbon, 1 oxygen, and there are 4 hydrogens, what we need to remember is hydrogen cannot be in the middle of the molecule. It will not be bonded to more than 1 element. But carbon and oxygen, they can form more than 1 bond. So they could be bonded to each other. And in fact, in this molecular formula here, there's only 1 carbon and 1 oxygen. So chances are that a carbon and oxygen, they are basically bonded to each other. We will fill in the electrons later. So they are like next to each other. Or in fact, you can go ahead and add the bond directly. So let's go ahead and put the 2 electrons between the carbon and oxygen, because there's a bond between the carbon and the oxygen. So we've taken 2 electrons from the 14. So we are left with 12 electrons now. And we have 4 hydrogens. Now, so those 4 hydrogens now, if you think about it, oxygen usually forms 2 bonds and it has 2 lone pairs. Carbon forms 4 bonds. So these 2 electrons, they represent 1 bond. This carbon should make 3 more bonds. The oxygen should make another bond. It should be bonded to another element. And what we're looking at here are 4 bonds, okay, 4 open bonds. And we have 4 hydrogens here. So one possibility here is that we just go ahead and include all the hydrogens on these bonds. So we have 4 hydrogens, and oxygen, since it's making 2 bonds, and notice how there's no charge overall, so 0 charge. So when oxygen has no bonds or no charge on it, it should have 2 lone pairs as well. And so we come up with a structure. And what we have to do now is we just have to verify if this is a reasonable Lewis structure. That means, does it match the valence electrons, total number of valence electrons, plus we have to make sure that it does not, none of the atoms exceed an octet here. So if you look at the hydrogens first, each hydrogen has only 1 bond to it. Each bond, remember, is 2 electrons that are shared between carbon and hydrogen. That means the octet is met for each hydrogen atom. Carbon has 4 bonds around it. So 2 electrons, 2 electrons, 2 electrons, and 2 electrons, total of 8 electrons, the octet is met. Oxygen has 2 bonds around it, 2 electrons plus 2 electrons, 4 electrons, plus 2, 6, plus 2, 8 electrons. So octet is complete. And if you count the total number of electrons, we're looking at 2, 4, 6, 8, 10, 12, and 2, 14. So that means this structure has 14 electrons total. There's no charge on it, which is what we see here. And the octet rule is satisfied for all the elements involved. Okay, so these are some things that we have to keep in mind. Now, the situation would be different if there were a positive charge or a negative charge in a molecule, but right now the octet rule is satisfied here. Let's try this out on another simple molecule so that we can work through this. Okay, so let's say we have a molecule where we have CnH5. Okay, and so again, what we're going to do here is we're going to count the total number of valence electrons. So number of valence electrons. Carbon is 4, nitrogen is 5, so 5 plus 4 is 9. 9, and then 5 hydrogens, that's 14. So I'm not showing the breakup now, but we have 5 electrons, 14 electrons. Nitrogen, so carbon is 4, nitrogen is 5, and for the hydrogens, we have 1 into 5. That's how many electrons we have here. Okay, so we've got 14 electrons again. And again, since we have a bunch of hydrogens here, they should all be on the periphery. We have only 1 carbon and 1 nitrogen, so they must be connected to each other. So what we can do is we can start with a bond between carbon and nitrogen. Now, the carbon should additionally make 3 more bonds. The nitrogen should make 2 more bonds. Okay, there should be 2 additional bonds here. And going back to the common bonding pattern, when nitrogen does not have a charge on it, it should have a lone pair. Okay, and so we have 5 hydrogens, and notice how we have 5 open bonds here. So we can go ahead and include hydrogens in all of these places. So now we have a reasonable looking Lewis structure. You could come up with other Lewis structures, that's a possibility, but this at least matches the molecular formula that we have given here. And I think if you came up with another Lewis structure, you might end up with charges. Okay, so there's no charge here. That's the thing here. And so now if we count the number of electrons total, we have 2, 4, 6, 8, 10, 12, and 14. Each bond is 2 electrons. one electrons from carbon, the other electrons from hydrogen. They're sharing electrons to make that bond. It's a covalent bond, okay? And if you look at each element, notice how each hydrogen has only one bond to it. That means its octet is complete, and hydrogen satisfies octet with just 2 electrons. Carbon has 1, 2, 3, 4 bonds around it. 4 bonds equals 8 electrons. So octet is complete. Nitrogen has 1, 2, 3 bonds. 3 times 2 is 6. So 6 electrons plus a lone pair, that's 8 electrons as well. So this structure overall has 14 electrons. So this is a Lewis representation. So the Lewis structure, as I said earlier, it shows us the connectivity in a molecule. It tells us which atom is connected to which other atom. So what we see here is that the carbon is connected to a nitrogen, and the carbon is connected to 3 hydrogens. Nitrogen is connected to the carbon, and it's connected to 2 hydrogens. And plus the nitrogen has 2 electrons in it. Now, this is a Lewis structure representation where we've used bonds. We can also show this using dots to represent electrons. So the carbon can be drawn like this. So it is basically another way of showing the same representation. So nitrogen has hydrogen, hydrogen, and hydrogen. Okay, so this structure should be read as this. Okay, electrons shared between carbons and hydrogens and everything together. So it again accounts for 2, 4, 6, 8, 10, 12, 14 electrons. So that matches the Lewis structure here. Now, in some cases, like I said, there might be a positive charge, so this needs practice. So please practice some. So in some cases, there might be a positive charge, and then you might have to account for that. And in other cases, there might be a negative charge, so you might have to account for that as well. Okay, so let's look at another example where we're going to have a positive charge. So now let's modify the structure that we're working on. Let's say this is CnH6, but now this has a positive charge overall. Okay, so CnH6, but there's a positive charge overall. So now when you count the number of valence electrons, carbon is 4, nitrogen is 5, hydrogen equals 1, but there's 6 of them, so that's total of 6 electrons. This is 5, this is still 4, so you're looking at 6 plus 4, 10, 15 electrons total. But wait, there is a positive charge, so you're going to subtract an electron for the positive charge. So this is again a 14 electron system. So when we end with the molecule, there should be only 14 electrons in the system. Okay, so again, there's carbon and nitrogen with 6 hydrogens. So we can start by drawing a bond between carbon and nitrogen. They must be connected to each other because it is a compound, a molecule. So they have to be connected to each other. Carbon additionally should have 3 more bonds to it. Nitrogen should have 2 more bonds to it. And it should have a lone pair to it if it were no charge. Okay, so we'll get to that later. So the carbon has 3 open bonds, nitrogen has 2 open bonds. Let's go ahead and include the hydrogens there. So we've got the hydrogens in all of those places. And now what you notice is we have a neutral molecule. And this molecule is what we had earlier. This has 14 electrons. But the problem is it does not match the Lewis, the molecular formula, because there should be 6 hydrogens. So where do we include that other hydrogen so that it will match the Lewis structure that we have? And so that the sixth hydrogen here, there's only one place where it could go. It cannot go and attach itself to the carbon, because the carbon is at an octet, 4, 2, 4, 6, and 8. It has a complete octet. It's not going to exceed its octet. So remember, that was one of the ground rules. It's not going to exceed the octet. Nitrogen has 8 electrons around it, but it has this lone pair. So one possibility is that the lone pair is actually shared between the nitrogen and this other hydrogen. So we get something like that. But now this nitrogen has 4 bonds to it. It is actually sharing its lone pair with another hydrogen. And so for that reason, this nitrogen is going to have a positive charge on it, okay? This is called a formal charge, okay? So this is a formal charge, and we can actually calculate the formal charge. This is given by the group number minus number of non-bonded electrons minus half the number of bonded electrons. Okay, half the number of bonded electrons. So this is the formula for calculating a formal charge. The group number of the atom minus the number of non-bonded electrons. This can be read as lone pairs minus half the number of bonded electrons. Okay, so if we calculate this for the nitrogen, a formal charge, the group number for nitrogen is 5. Okay, group number for nitrogen is 5 minus, are there any non-bonded electrons around the nitrogen? Non-bonded, read that as lone pairs. There aren't any. So 5 minus 0 minus half times half of the number of bonded electrons. How many bonded electrons do we have? We have 2, 4, 6, and 8 bonded electrons around that nitrogen atom. So that's half times 8, which is basically 5 minus 4 equals 1. So we get a formal charge of 1 for that nitrogen atom. So that's why it's a plus 1. Now, just to show you this, let's also calculate the formal charge for this carbon and make sure that carbon should not have a charge on it. So if we do this for the carbon, group number for carbon is 4 minus number of non-bonded electrons, that's 0, minus half into 8, because there are 2, 4, 6, 8 bonded electrons around the carbon. So this is 4 minus 4, which is 0. So the formal charge on this carbon is 0. That means for this molecular formula, given molecular formula, there is a positive charge somewhere in this molecule or the compound, and that positive charge we've calculated is on this nitrogen atom. Okay, and the system overall has 14 electrons, because you can see there's 2, 4, 6, 8, 10, 12, 14 electrons overall on the system. So that positive charge actually ends up on the nitrogen. Now, when you calculate the formal charge, if you get -1 or -2, that would mean that there is a negative charge on that atom. That's how it works. So hopefully this helps you, this will help you actually calculate the Lewis, or come up with the Lewis structure for a given molecular formula, and then calculate a formal charge for any atom that may have it. Okay, there is going to be a handout that will go along with this, which basically lists all these rules and everything. So use the handout, and additionally use this the video lecture to help you through this process.